So hello. Yeah. I think it's already 3 times hello. But anyways, so today we have us with Krisztina, and she will talk about polynomial kernel for face cover on non-embedded planar graphs. So yes.
Yeah, so this is actually a paper that I started writing in the second year of my PhD, and then once we thought we were done, and we started like preparing it for publication. Then we found a mistake; the entire project fell apart. But then we revived it a few months ago, and we actually managed to like fix the mistake, and we managed to actually get this polynomial kernel. So yeah, the title is Polynomial Kernel for Face Cover on Non-Embedded Planar Graphs. So this non-embedded planar graphs might sound a bit weird because sort of by default, a plane graph is the embedded version of a planar graph, but we just wanted to emphasize the non-embedded part because it's kind of the important part of the problem that we are working with. So let me first define the problem. So the face cover problem, we are given as input a planar graph. So just a graph as an abstract like list of vertices and edges without an embedding, and we are given a set of terminals that are a subset, that is a subset of the vertices of the graph. And we are looking for the size of the smallest face cover, and the face cover is just a set of faces that covers all the terminals, and where a face covers a terminal if a terminal is on the boundary of a face. So here is an example. We are just given some graph as like a list of 6 vertices and these edges and these terminals. And we might draw it like this. This is just one like planar embedding where the red vertices are terminals. And in this embedding, we cannot cover all the terminals with one face. We need two. So for example, we can take the outer face and this inner face. So in this case, we don't really like differentiate between this like infinite face that is sort of around the whole graph versus like all of these like sort of finite faces. We just don't care. Everything is just like one, counts as one face. But what you may notice is that we can also embed this graph in a different. Okay, I hope the colors are kind of visible. So this is the red vertex and this and this. I don't know why is it so like why is red so hard to see? Like
it's always hard to see.
Okay, good to know.
Never use red, please.
Okay, good to know. Well, I think in later slides I have also squares
Another combination of red
instead of red. But yeah, so what you may notice is that here this edge is kind of not in the best position. We could just sort of pull it out, and we can get a graph. We can embed the same graph like this. So we just took this edge v2, v4, we sort of pulled it out, and now we can cover these 3 terminals by one face. So in this case, for this graph and this set of terminals, the face cover number is 1. And so this is our task, so finding the smallest face cover, but it also kind of includes finding the best embedding in which achieves this face cover. So what is the motivation for this problem? Well, this face cover is very useful as a parameter for many problems. So for example, for edge multi-way cut, in which we are given a graph with weighted edges and a set of terminals, and we want to find the smallest edge cut that pairwise separates all the terminals, and there is an n to the square root of k algorithm for this, for example. Another example is shortest non-crossing walks in a planar graph, where we have, again, a graph with weighted edges and t terminal pairs, and our goal is to find the non-crossing paths of minimum total length. And there is also there is an algorithm parameterized by face cover and the number of terminal pairs. Also for Steiner tree, there is 2 to the k times n to the square root k times algorithm. And there are also many other examples, because very often sort of if we have some problem with terminals on a planar graph, it becomes much easier if we know that the terminals all belong to one face or to like a small number of faces. So basically, our motivation is that this is used as a parameter, but we don't really know how to compute it. If you're just given a graph, we don't know, like, and the some set of terminals, it's not immediately clear how to compute this. So what were some previous results on this topic? In 88, Beanstalk and Monma came up with a C to the k times n algorithm for computing face cover. And that is pretty much it when it comes to this like non-embedded version. There was more work on an easier version of this problem where we are given a fixed embedding. So we're not just given a planar graph, we're also given an embedding. And in that case, there are some better results. And there is also a linear kernel. Another thing that was shown before already by Beanstalk and Monma in the 80s is that without loss of generality, we can assume that our input graph is biconnected, because it is very easy to reduce the one connected case to the biconnected one. So what will we do? We will use for constructing this kernel, we will use this weird data structure called SPR-trees, which is some sort of a way to describe all the embeddings of planar graphs, and basically it describes how planar graphs can be constructed from like smaller parts. So a bit of background. Okay, hopefully you all remember that a tree-connected graph is a graph where you need to delete at least 3 vertices to disconnect it. And there is a theorem by Whitney from the 30s that a tree-connected planar graph has a unique embedding. And unique here, of course, does not mean like geometrically unique, because of course, if you just slightly move some vertices, you get like a slightly different embedding, but unique in a combinatorial sense, namely that the set of vertices that correspond to faces are unique. And using this theorem, we can actually construct these SPQR trees that describe all embeddings of biconnected planar graphs. So basically what SPQR trees do is they tell us how is our graph constructed from some like small building blocks. And the building blocks in this case are tree-connected components because they have a unique embedding, and single edges because we also need this case for the, basically if we want to construct something that's not tree-connected. And the SPQR trees also describe how do we construct our graph from the tree-connected components and single edges. So what can we do? How do we construct planar graphs? Well, what can we do? We can take some smaller planar graphs and connect them in different ways. So one of the ways is to connect them in series. Basically, we kind of construct a cycle where we glue together our planar graphs like this. Another way is to connect them in parallel. So we just take 2 of their vertices and somehow connect them in parallel like this. Then there is this sort of boring edge case of just literally one edge. Yes. That we did just as a sort of leaf of the SPQR tree. And the last way to connect the parts is in this rigid way, which means that we take some smaller graphs and we connect them in a tree-connected fashion, basically.
So why is it a letter Q and not B?
So it is Q because I think the only reason is because they wanted to make this acronym SPQR, which means something like Senate and People of Rome. Why? I don't know. But I guess because SP and R were already there, so might as well. Yes.
So the rigid is that you have this rigid graph and edges. The underlying original is rigid. That's what you do. And then you replace every.
Yeah. So basically, yeah, you take some sort of some tree-connected graph, and each of its edges will be replaced by a smaller graph, sort of.
but it's for all the others. Right?
Yeah. So this is how we construct an SPQR tree. Basically, we start from leaves that are either tree-connected graphs or just single edges, and the vertices of this tree describe like how do we connect the sort of the children of each node, and then of course we can to each of these nodes we can associate sort of the graph constructed so far. And like this is the sort of way to do some sort of dynamic programming on planar graphs is basically we start from the bottom from leaves, and then we talk about like if I have an S node, what do I do, and so on. So some vocabulary that might be useful is if we have a node in the SPQR tree, the node skeleton is basically this graph that describes sort of how do we connect the children of this node. Another thing is if we have some node of the SPQR tree and we just focus on one of the children of this, then sort of from the point of view of this child, it has these two important vertices that sort of tell us that, oh, these are the vertices where we attach this to the rest of the graph. And this edge, kind of the edge between these corner vertices that we call corner edge, that is the edge that kind of represents the rest of the graph. So the rest of the graph, like from the point of view of this component, the rest of the graph is just something that will be like on this dotted edge. And the external faces are the faces that are adjacent to this corner edge. And these faces will be very important because these are sort of the reusable faces of this component. So these are the faces that sort of can be used, that are sort of the outer faces of a component, and that can be used also to cover some terminals, both like in this component, but also like they can be used to cover some terminals in the parent and so on, like in the parent components. So how do we get the embeddings of a planar graph from this SPQR tree? Well, like there is not much that we can do. Basically, what we can do is we can just flip. So we can take any of the children component, we can just sort of flip it, like in this case, kind of horizontally, like when you look at this corner, these two corner vertices, and then we just flip this. And another thing that we can do is if we have a P node, we can just reorder arbitrarily all of its children in just in any order that we want. And that's basically it. So, okay, what do we actually do in this paper? We look at how to kernelize this face cover problem. So hopefully all of you or most of you know that what is kernelization. Well, the idea is that we want to create a smaller instance that is equivalent in some sense to our input instance. So in this case, we want to construct a smaller graph with the exact same face cover number. And what does small mean here? It should be polynomial in the size of the face cover number. Or in our case, it will be cubic in the size of the face cover number. So, okay, step 0, as you could maybe guess, is we construct an SPQR tree. There are some polynomial algorithms that do this. We didn't really get too much into it. We just use it as a black box, and we assume that this decomposition is given. So, okay, what might be the first attempt is to say, like, okay, we just start. We look at the leaves. We construct some kernels for them. Then, using that kernel, we go up the SPQR tree and do this like sort of inductively from leaf to root. So, okay, if we just say, okay, let's just take a subgraph that corresponds to like a child of a node, and we just replace it by a smaller graph that has the exact same face cover number. Well, the problem is that if we do this, so if we look at this blue graph, so the red squares are the terminals. So this blue graph has a face cover number of 1 because you can use this rectangular face to cover all its terminals. And we might want to replace it by this blue triangle that also has a face cover number of 1 because this triangle, like triangular face, covers this one terminal. However, what you may notice is that in this whole graph has face cover number 2 because you need this rectangular face and also, for example, this one. But in this graph after the replacement, it has face cover number 1 because you can just use this sort of one face that covers both of its terminals. So this is something that we don't want because we just, like, even though we preserve the face cover number of the smaller graph, like after the replacement, the whole instance ended up having a smaller face cover number. So this is not what we want. And the reason, sort of what is kind of the problem here, is that although these two graphs have the same face cover number, the difference is what faces are used in this face cover. So here, the face that is used is this internal face, and there is no face cover of size 1 that uses just an external face. And here we can either cover it by this internal face or any of the sort of outer faces of the external faces. So this is somehow what made the difference, because this internal face is not sort of reusable. It's just a face of this graph and nothing else. While these external faces like this, they are sort of reusable because they also cover some other stuff. For example, this terminal in particular of the bigger graph. So we see that we need to really distinguish between these internal private faces that cannot be reused and external faces that will be reused. So basically what we see that we need in our inductive construction is we need the replacement graph to preserve face cover number, but also given that we use 0, 1, and 2 external faces. So in all of these 3 cases, the face cover number has to be the same as the original one. Then the next thing that we might want to do is, okay, we just look at this blue graph and we just look at its face cover number. But the problem here is that if X here is a terminal and it is also a corner vertex of the blue graph, X might be covered sort of from the outside of this blue graph. So it might be covered maybe by this face or by this face. And these are the faces that the blue graph is sort of not really aware of. Like the blue graph is only aware of like its own faces and these two like of its external faces. And it's not aware of a face like this. So we also need to sort of to take into account this case. And the way that we do it is that we compare the face cover of the original graph and the newly constructed graph also, and they also need to be the same in case where the corner vertices are not covered. Okay, the third attempt would be to just say, okay, I have, like, for example, this big S node that has a bunch of copies of these graphs. And what I want to do, and I maybe have a lot of copies like k squared or like even square root n or whatever. And what I might want to do is to say, like, okay, each of these children of the S node will be replaced by a smaller graph that has exactly the same properties and preserves the face cover. But the problem is that we might have a lot of these components. So in this case, I can have arbitrarily many of these small graphs. The face cover of the entire thing is still 2 because I can use sort of this face. And so I can use basically the 2 external faces. So the face cover number of is 2, so I cannot just discard it and say this is a no instance. But if I want to preserve the face cover that uses 0 external faces, so the face cover number that uses 0 external faces is k-squared in this case, because we need to use the square face. We're not allowed to use the external faces. We need to use the square face in each of these small parts, which means that basically no matter what I replace each of these small parts with, even if I replace it, I mean, it's already a constant, even if I replace it by like even 2 or 1 vertex, like it's still not enough, because I still could end up with potentially with like too many vertices in my graph. But what we notice here is that we could say that, okay, the face cover number that doesn't use external faces is just too big. Namely, it's bigger than k. So we know that this is kind of not what we need. So it's basically enough to just say preserve the face cover number if it's at most k, or just preserve that in the original graph it was bigger than k and it is still bigger than k, and that's it. We don't have to preserve it exactly if it's bigger than k. It's enough to just say like, oh, it's k plus 1 or more. So okay, finally, like after solving these problems, we get to the definition of a small nice kernel. So k is a small nice kernel of GT, which is the sort of this partial graph that we constructed so far that corresponds to a node in the SPR-tree. So it's a small nice kernel if, okay, first of all, we have to preserve the corner vertices and the corner edge, because these are the ways that we attach it, that we can insert the kernel into the bigger graph. And then we have to preserve these properties, the face cover number, this FCM 0, 1, or 2, those are the face cover numbers that use 0, 1, or 2 external faces. So as I said before, they need to be either sort of the face cover of the kernel needs to be either the same as the original and smaller than k, or both of them need to be bigger than k, and then they don't need to be equal. And the same needs to hold in k, for the case where we sort of pretend that the corner vertices are not terminals. So when we cover everything but the corner vertices, we need to preserve the same property, that either both of the face covers are equal and at most k, or both of them are bigger than k. And we call a nice kernel small if it is if we need so if we need this many internal faces in the face cover of our graph, and basically this condition of like being small, this is what will give us this cubic kernel, like, because we will do this inductively, and in the end we end up with a sort of a cubic kernel for our problem. So our approach is to have like 2 types of reduction rules. We will have some basic replacements for different types of components, for the terminal-free ones, unproblematic, semi-problematic, and problematic. And then we will have some node-specific reduction rules differently for SP and R nodes. So a terminal-free component, as you would expect, is a component that has no terminals except for possibly the corner vertices. And these are kind of the most boring ones. We just replace them by a single edge, because the only thing that we care about is that this is something that is on the boundary of a face, and it's somehow like, we cannot really erase it, because then we would merge some faces, which is not what we want. But it's enough to preserve it that, oh, there is just this connection between these 2 corner vertices, and we don't care about anything else. So this is the easiest case. The next easiest case is an unproblematic component, which are those that can be covered by 1 external face. So for example, this blue one, if you see that all the red terminals, they belong to this face. So we can replace it by a terminal subdivided edge, namely we just take its corner vertices, we connect them by an edge, and we add like a terminal in the middle of this edge. And this, after the replacement, we still have the exact same property. So this graph can be covered by either one of these external faces. Okay, then the semi-problematic components, those are sort of a bit strange. Those are the components that can be covered either by two external faces or by one internal face. And there we have this kind of strange trade-off, because either I want to minimize my face cover sort of immediately, and I want to say, okay, it should be one because one is smaller than two, or I could say like, but maybe it's better to use faces that are reusable later on. And we want to preserve this exactly. So we want to replace it by something that has exactly the same properties, because we don't want to decide immediately whether we use like this sort of private face for this blue graph, or we use maybe these two external faces. So what we do is we replace it by a gadget like this. That again has the same property, namely the two terminals can be either covered by this internal face or by these two external faces. And finally, we have the problematic components, which are basically everything else, and we will deal with them just by induction. Okay, so those were the sort of basic reduction rules the basic replacements that we just do like in all of the nodes of the SPR-tree, and then we have some like node-specific rules. So for S nodes, those are these ones. What we can do is, if some of these sort of smaller graphs just consist of one single edge, then we can just contract this because we don't really like care like these edges like don't influence any like the embeddings or anything else. Then the next thing that we can do is, if we have at least k+1 unproblematic or semi-problematic virtual components, so virtual components are these children of the node, so we can contract all but k+1 of them. So this is this sort of what I mentioned earlier about we need to preserve the face cover number, but only if it's at most k. And if it's bigger than k, then we just say, okay, it's k+1, and it's at least k+1. We don't care like how much exactly it is. Then the p nodes are also relatively simple. Because if we have some of these components that are just a single real edge, we can just delete sort of all but one of them, because you can think of it as, so since we can permute arbitrarily these children of the p node, we can just group together all the real edges and just treat it as just one real edge. Then the other thing is, for the same reason, we can do the same for the terminal free components, and then by like a relatively easy counting argument, we see that if there are at least 4k+2 virtual components left, then we have a no instance. So basically, for both S and P nodes, relatively easily we get to a situation where we just have sort of O of k children, and that's it. So for R nodes, the situation is a bit more complicated. So what we can first do is we first observe that if a face has a lot of terminals, it has to be in the face cover. And sort of the idea behind this is, if you have a face with a lot of terminals and it is not in the face cover, then you would have to cover all these terminals by some other faces. And like because of this tree connectivity and everything, you would need more than k such faces. So if a face has more than 3k+1 terminals, then we already know that it's in the face cover. So we might as well say, okay, forget about all but 3k+1 of these terminals and just turn them into non-terminals, because we already know this face will be in the face cover, and that's like all the take care of it. And then the next reduction rule that we have is to delete edges that are on boundaries of faces that have no interesting vertices. And interesting vertices are sort of either the corner vertices or terminals. But this is very dangerous because deleting edges breaks tree connectivity. So we have to do this like somehow very carefully, because also breaking tree connectivity also implies that we could potentially have more than one embedding, and suddenly sort of things stop being rigid, and suddenly we might be able to do something in the sort of newly constructed graph that we were not able to do before. So how do we overcome this problem is that we say, okay, we will temporarily work with this embedded face cover. Namely, we will treat this problem as the face cover problem where we are given a graph with its embedding, and we are not allowed to change this embedding. We just want to compute the sort of best face cover in this fixed embedding. So then we can, like, working with this like embedded face cover, we can also have some more of the reduction rules that are sort of relatively intuitive. If I have two faces that contain exactly one interesting vertex, for example, they contain exactly the one terminal that is the same and nothing else that we care about, then basically I don't care whether I use f or f prime in my embedding, and I will never want to use both of them because they cover exactly the same thing. So I might as well delete the shared boundary and merge these two faces together, because I know that in the solution I will use well, potentially either f or f prime. I will not use both of them, and potentially I might not use either of them, but this is still fine. Then the next thing that we can do is in this construction we get some longer induced paths, and if they contain no terminals and no interesting vertices, we might as well replace them by a single edge. And finally, we rigidize the embedding again. So this is like a known procedure on how to make a graph tree connected in sort of a very controlled way. So the way to do it is if I have this vertex that, for example, has these two neighbors. So if I start with this like black three vertices and two edges, what I can do is I can create two copies of each of these edges. These are these pink ones. So I add these copies of the edges, and I also add a cycle around this vertex, and I sort of add these pink vertices in the intersection, and this somehow rigidizes my graph and makes the graph. So, and I repeat this procedure sort of around every vertex that breaks the tree connectivity, and by doing this, this somehow rigidizes the graph, and I can no longer sort of move this in any way. And that's basically it. We get a cubic size kernel, which is the first polynomial sized kernel for this problem. So it's interesting to note that in the special case where we are working with a fixed embedding and all the vertices are terminals, in that case we can get a linear, people can get a linear kernel, so not by our algorithm, but these are some of the previously known results. And we also know that from literature that there is a sub-exponential algorithm for fixed embeddings for the face cover problem. And what is open is whether we can get a linear kernel for this non-embedded version. So for S and P nodes, we can get something that's size that has size linear in K, but the R nodes are more problematic, and we don't really see a way on how to reduce this cubic kernel to a linear one. And another open question would be whether there is a sub-exponential algorithm for the non-embedded version. And this is actually this was actually the initial question that we wanted to study, and the sort of motivation for studying kernels, because sort of experience shows that if you have a problem on planar graphs that has a linear kernel, then very likely there is a sub-exponential algorithm for it. But I also don't know, like, if there is some sort of what is the reason behind this intuition? Is it just sort of a coincidence? It could be, but yeah. So we are interested still in whether there is a sub-exponential algorithm for the non-embedded version, and that's it.
So I think for the unproblematic case, can you go back to that slide?
Yeah.
No, I think one more. I think here, so you could have just added a 4 cycle. Why this extra 2 vertices in the middle, like right to A and left to B?
So let me think. If you add a 4 cycle, then what is the problem? So yeah, maybe you're right that we could do it also with a 4 cycle. Yeah, I think so. Yeah, good, fine. Any other questions?
Yeah, a bunch, but so I could follow, but at the same time I was thinking about other related things. So not sure if you said it. So you have, as you have the kernelization, there are some reduction rules to get you towards some sort of kernel.
Yeah.
Do you know if you can, like, does it matter in what order you do the kernelization steps? But if you go like, maybe you said it. No. So if you go like try a bunch of stuff there, a bunch of stuff there, will it converge to the same thing eventually? Probably.
So I think for I think if you just for our nodes it's more tricky because there you actually have to do it in the right order, sort of to break this tree connectivity sort of at the right time. And I think for SNP nodes it doesn't matter as long as you apply everything exhaustively. I mean, no. So in the SNP nodes, I think maybe sometimes you would have to sort of go back to sort of the previous reduction rule and repeat it. And
so you take the tree and you go from the leaves.
Yeah.
Okay. So that's very good. And then it shouldn't matter whether you do it on the left or on the right first.
So in that sense, yeah, that shouldn't matter. Like from or like I don't know. So that shouldn't matter. But if you like look at like one particular child and then you look at the reduction rules for it, this matters in the R nodes because you want to break this tree connectivity at the right time. And yeah.
And there's a unique kernel for that, for each.
Sorry.
The kernel is unique or no? No. There's multiple.
I mean, there are rules like
big
equals one terminals and the other.
Sorry, I was in my head somewhere and there at the same time. Okay. So do you know what's the structure of the kernels? Like, is there some way to compare the kernels? Pick a better one in some sense.
But I mean, so they're basically all the same. Like, what does a better one mean? Like, if they're all cubic, rough. I mean, okay, some I don't know. Like, if some of them could be slightly smaller, but
it's not just size that matters. The one would be with maybe.
So how do you choose the prettiest?
One could be with a bounded tree with or something, right?
Yeah. So I don't know. We never really thought about like comparing different kernels and whether what is the sort of best one that you can get. So, but yeah, this is an interesting question. Yeah, Michal, you had a question.
Yes. Question is like nothing. Okay, so together with the kernel, do I also get some kind of like solution lifting back? Because like
I bring you a graph, you give me a kernel, and all I can do is like compute the base cover of my graph or of the kernel, but can you then give me back the kernel of the original?
No, the solution
Yes.
of the original.
Yeah. Oh yeah, the
Yeah.
solution.
Yeah, I think this. Okay, I have to think. So for most of the reduction rules, it is kind of clear what to do. So I think there should be a relatively easy way to sort of reconstruct this solution from the solution of the kernel. Yeah. But yeah, I mean the other thing is also the question is whether you just get so if you solve the kernel, do you also get an embedding, or do you just get a number as the output? I think this also should make a difference.
So the kernel is still free connected, or it might not.
No, so I mean
it was not.
Yeah, it was so the kernel of the R nodes is tree connected as it was, but the whole graph was not tree connected. So yeah, the kernel is not tree.
Not that I would like to implement it.
Yeah, so I actually don't know, because these SPR-trees, the references for them are horrible, and somehow everybody defines them in their own way. There is no like consistency in the literature, and I also have no idea how do you like what is if there is a good way to actually compute an SPR-tree from a given graph.
Yeah.
So if there are no more questions, let's thank the speaker again.